Good evening, everyone. Am I audible to all? Anyone can unmute and respond. Okay. So, welcome to the week one of the live interactive session of the fabrication techniques for MEMS-based sensor, a clinical perspective. The course instructor is Professor Hardik Jitendra Pandey of IISc Bangalore, and I am the PMR of teaching assistant Vikas Pandey from IIT Jodhpur. So, this is a brief about me. I am a PhD scholar in space science and technology at IIT Jodhpur. I've done MTech in VLSI, with BTech in electronics and communication, and I have also worked as R&D engineer, online faculty, and robotics training. So more you can find in the on my portfolio. And the schedule for my classes will be Tuesday 6 p.m. to 8 p.m. And the link for meeting will remain the same, which is given here. Anyway, the slides will be shared, and you can access all of these contents. The recording of these classes will be available on the YouTube channel mentioned here. And for any query or any question, you can email me also using this link. So before moving forward to questions and other things, I would like to ask you people if you have any doubt or questions related to the things taught in this week, you can ask, as well as you can discuss some basic things which you are not like you have some confusion. And the purpose of this whole session is that you can interact, you can ask questions, you can clear your doubts. That is why I'll not be taking questions from chat. I will be taking questions directly, uh, so that you can unmute yourself and speak up. So please feel free to unmute and speak up. Any questions or any doubts, please feel free. Hello. Uh, if no doubts, we can move forward. But I'll welcome any one of you having any doubt or any basic question also, not an issue. Okay. So let's assume that there is no question. So we will be moving forward to some questions. I'll be taking some questions related to the problems. They are not exactly the assignments that are given this year. They are mostly assignments given in the previous years, as well as some extra questions, so that we can understand the things. So the first problem is the term IDE in this course stands for interdrug electrode, interdigitated electrode, integrated development electrode, or investigational device exemption. Anyone? Option B, interdigitated electrode. Good. Anyone with some other answers? Don't be shy, please speak up. And even if you are wrong, it is fine. In learning, if we are wrong, it is very helpful, because if you are wrong, you will remember the next time what is the correct thing. Okay. So please feel free to speak up. Okay. Anyone? I think Shuparna Sudarshan, are you there? Shwat, Shwati, hello. Option C, why? And I think Varsa, you replied B, right? Okay, so be ready with Y also, the answer for Y. Okay. Yes, someone said C. Why? Yes. Okay. Uh, Anyone else with any other answer? Uh, Answer B is the correct one. And why is it correct? In fact, sir has also shown in the lecture when we talk about ID digits, like if we see this image, it was zoomed there also. It have digits or electrodes like this. They look like the fingers or digits, okay? Alternates like this, okay? And they are connected like this. They will be connected, okay? And since they look like digits and they are uh, like alternates, that is why they are also known as interdigitated electrodes, and they are very commonly used in making sensors. Okay, any doubt regarding this? Let's move forward. Okay, this is a statement. You have to tell whether it's true or false. Immunotherapy is a therapy that will activate your immune system. Is the statement true or false? Yeah, please. True. Okay. Why, like, do you have idea what is immunotherapy? Mhm. Yeah, please continue. Yeah, I was unable to like get the complete thing. I think you said something, but half of it. Yeah, completed. Good, but not block. They will unblock the immune checkpoint, right? Yeah. Anyone else would like to add something to this? Certainly, it is true to activate our immune system. This fine. But anyone who knows something more about immunotherapy, this is the term we have heard in the class also, right? So, uh, see, the traditional, like I am taking an example of cancer therapy since sir has also taken that. What it does is that it kills the cells that are present, wherever there is a cancerous cell, we try to irradiate it or use drugs or either C60 radiation or some drugs that will try to kill the cells that are present in that area. Okay, so this is the traditional method. But what if we could increase our immune system, like let our immune system do this thing, so it identify which one is our natural cell and which is cancerous cell, carcinogenic cells. Okay, so the ways like in which we can use the power of our own immune system by giving it some medicines and some drugs that will activate our immune system and it will try to get rid of the cancerous cell. Such therapies are called as immunotherapy, and they are mostly like being employed, especially in case of cancer. Not fully, they are still in trial phases. Okay, so yes, it is true that it is a therapy that will activate our own immune system to take care of the diseases that that we are at present doing with medicines or drugs. Okay, so let's come to problem three. we have seen that this whole course is about sensors, biosensors, or MEMS-based sensors, you can say. So the smallest change in input, like where the stimulus or the thing that we are measuring is changing in a very small amount, which a sensor can detect and express as an output, is called which of the following: specificity, resolution, sensitivity, or none of the above? Resolution, good. Uh, Anyone else? Please speak up. Don't worry if you are wrong, or what if someone will say something. Don't worry about it. Please speak up. And I would like to know what is the general level of the audience here. Like, can you all say in which, what is your educational levels, so that it will be very easy for me to understand. Okay. I think Versa, what is your educational level? Okay, use in which department? Okay, great. Uh, Arti, Arti Sekar. Let me see. Yeah, what is your present educational level? Okay, BMA means. Okay, okay, great. And Swati, yeah, you can unmute and respond. Swati, okay, she might not be here. Then I think Anjusri, are you there? Hello. You can unmute yourself one by one and speak up. Like, what is your present educational level, so that I can understand that what is the general audience. Okay. So two people, they are in second year. Fine. Uh, Anjusri, am I audible to you? Okay. Aruloli, Aruloli K. Arti already have responded. Saranya Jagan. Hello. Yes, yes, please. Okay, great. Okay. So you must be aware with these basic things, right? Okay. Mm-hmm. Okay, great. Yeah, someone has responded on chat also. I think Anjusri completed MTech in instrumentation and currently effective. Great. Okay. Uh, Other, just a minute. Hello. Yeah. Other, I think Saranya, you have not responded, right? Saranya Jagan and Saranya Satish. There are two people. Yeah. Saranya Jagan. Saranya Satish. Yeah. Okay. Anyway, so I will assume most of you are at least undergraduate, right? So, you must be aware of about sensors and what is sensor? Like any any physical thing, physical or chemical changes which we can detect and convert to electrical signal in a simple sense. Electric, there are physical changes, physical or chemical, especially in case of biosciences or clinical uses, we have chemical changes which we want to detect using a sensor, and it gives an output in the sense of electrical signal which can then be processed through our computer system or whatever processing system and can be displayed. Like, can anyone give an example of a basic sensor we use in our daily life, or at least we tend to use? You must have seen your parents using or grandparents using. Anyone, please? I am audible to you. Hello. Yeah. Okay. So, can you give some example of a sensor that we generally use? Like, have you seen glucometer? Anyone, if you to check diabetes and all? You can raise your hands also. I think there is option of raise hand, right? Have you seen glucometer? Okay, connects you have not seen. Okay, so if you can check, there are basic sensors available in like we use in daily life also, including if you have an AC. Let's go to very simple sensors. If you have AC in your house, you must have seen that the temperature is displayed, or if according to the temperature, the AC will switch, like either it will increase the speed or decrease the speed. This is done with the help of a very simple sensor, that is a temperature sensor. Okay, very similar to that, in biological world also we need some sensors, to detect the blood glucose level, to in fact a lot of things that are at present not done exactly using sensors, but the approach is that we could implement all of the things using sensor. At present we do like heartbeat analysis, or you can see using stethoscope. Okay, that is still manual. There are attempts being done to even listen to that and using some sensor, and so that we can directly get a graph or something that what is wrong or everything is fine or not. Such things which can detect some physical or chemical change in the real world and convert it into electrical signals are called as sensors. So the minimum change that we can detect, like the smallest change we can detect, is known as resolution, which I think Versa said, right? So the smallest change in input which a sensor can detect and expresses in output is called as resolution. Anyone knows what is specificity? Anyone, please? Or sensitivity? Please respond. If you respond, then only we will be able to have this interactive session. Okay. Otherwise, it will just be a lecture. And we have adequate time. Yeah, please. So it is almost like resolution is the you can say the minimum sensitivity is the resolution, right? Okay. Yes, and other continue. Specificity you were saying. Yeah. Mm, mm. Yes, very good. Like in general, like when we talk about sensors, like say generally I work with gases, so I will give an example of gas. Okay, that suppose I am making a sensor to make a hydrogen sensor. Okay, but the same sensor is also there is no perfect sensor. Like it will detect only and only hydrogen, but it will not detect other things. That is not possible. It will detect other things, but in less quantity. Okay, so specificity will be if the detection of hydrogen is highest, like maybe for 1% hydrogen, it can give a response of say 80%, 80% change in electrical current. But when ammonia, like ammonia or other gas like CO2 or any other gas, let's say NH3, this comes, it will, for the same amount, it will give very less response, maybe 1% or 0.5%, something like that. Okay. So in this case, we will say that this sensor is specific to H2. Similarly, like if we are going for biomolecules or something like specific biomolecule is like that sensor is very much responsive or very sensitive to that specific biomolecule and not to others. And that is called as specificity. There are some proper terms for this, like when we compare them, like how much specific it is. But for now, we just need to know the definition that specificity. So, what will we need? A more specific sensor or less specific sensor? More specific sensor. And resolution should be high or low? Okay, so if the resolution is very high, like I know when we say resolution high, we say that we can see very small things also, right? So in that sense, we will say the resolution, the limit should be very small, the smallest change, right? So it should not be very like in general terms, we say it has high resolution, but the quantity should be small. In a sense, we talk in sense of reverse of it. Okay. So, and the sensitivity should also be very high. Resolution should be like the smallest possible resolution. If it is there, it is the best. Okay. Moving forward, okay, here is a very common question. What is the most common set of commercially available silicon wafers? Have anyone seen silicon? I think someone was talking about he is doing uh, after PG he is doing research, right? So you must have seen silicon wafer. And sir also showed in the video lectures. Yeah. So can anyone tell me what is the shape of the silicon wafer, commercially available silicon wafer? Is it a square, circle, or rectangle, or a triangle? Circular in shape. Okay. Any reason why it is circular? If you go into the like how silicon is prepared, how the silicon wafer we use is prepared, you will understand that why actually it is circular in nature. I think that is not covered in this course. That will be a different course. Okay. But in general, we see that silicon wafer comes like this. And seeing the silicon wafer, like since I think some of you are from electronics background, you must be knowing that the semiconductor, silicon semiconductor. In fact, most of us we study in intermediate that they can be either P type or N type, right? Is there any confusion in that? So, in general, we will have a circular disc kind of structure, and its diameter can vary. It comes starting from, I think, 1 inch, I'm not sure, but 2 inches, 3 inches, 4 inches, 6 inches, 8 inches, and nowadays even 12 inches silicon wafers are available. Okay. And as the size increases, the thickness will also vary. They come in circular shape, but there will be some cuts. Like sir was also showing that there are primary cut and secondary cut. Like there will be a big cut this side, and there can be a small cut here or here. So based on that, you can identify what kind of wafer it is. If it, in general, we use 100 wafer. So if it is on the opposite side, primary and secondary cut, it will be an N-type wafer. And if it is at 90 degree, it will be a P-type wafer. If it is at 45-degree angle, you can understand it is a 111 N-type wafer. And if it is having just a primary flat, then it is 111 P-type wafer. So it is circular in shape with some small cuts on it. Like, okay, fine. Any doubts still here? You can ask. See, most of the these wafers are the base of our sensors, you can say. Nowadays, we have gone into other materials also, but most of the conductive, you must have learnt about conductors and insulators, right? But there are some materials which can be tuned to work as conductor sometimes and sometimes as insulator. Okay, so using this property of these semiconductors like silicon and germanium, we are able to make a variety of devices, including the computer we are using to interact or the mobile. The processor of it is made up of using silicon. Okay, so all these things are made on this silicon wafer only. Okay, all the uh, most sophisticated electronic devices and including the sensors also. So we will be using this wafer as the base of our sensors. Sometimes we will be using them as like we will be using their conductivity, but mostly what till now sir has shown is that we are using a insulator above it, like SiO2, and then we are making the sensor over it. And one more advantage of using silicon is that since silicon manufacturing, silicon fabrication, silicon based fabs are already quite developed, quite advanced. Okay, like we have, you must have seen that nowadays we are talking about 5 nanometer, 3 nanometer processors in our mobile phones. Okay, so that is already quite advanced. So using the same facility, we can make our sensors also. That is why we mostly go for silicon wafers. Though it can be, if we are not using the conductivity of the silicon, we can go with other things also. Like we can go for glass, and there are other kind of options also. But silicon, actually, it is very already quite in a quite advanced state. Like we can get a very pure silicon wafer, and we can make a sensor over it. And we will be seeing in the next lectures also, like how clean environment we work, like clean room, how is it maintained, and this thing. So you will get an idea that if we go with some other things, we'll have to make that whole thing again for that specific thing. And with silicon, we already have the option. There are fabs already available. That is why mostly for sensors, we go with silicon wafers. Okay. Uh, Okay, now again we come to the interdigitated electrode. It can be used to measure the DC resistance of the material placed on it. Is it true? Can only DC resistance of the material. Yes, please. If you are not understanding anything in the question, you can ask that also. No. So we have seen interdigitated electrode. Okay, so we can say a metal like this. Okay, and then let's first understand only with one. Okay, one finger, one digit. This is a metal. This is another metal. Okay, so this is a simple interdigitated electrode, and if we go like if we make it a bit more complex, it will have more fingers. Okay, so as we know that if we have such finger, what will be the like? Will there be any current flowing if we connect this to a positive and this to a negative? Will there be any current flowing through it? Yeah, please. Anyone? These are very basic things, right? Please speak up. Gokul Anand, are you there? Yeah, please speak by unmuting yourself. I cannot see the messages. Hello. Please unmute yourself and speak. So, what do you think if there is one metal line like this and another like this, and there is some gap, and if we connect to a battery or some source, will there be some current flowing through it? No. Why? There is a gap. Okay. Now, suppose we put a material over it, like say we put some biomolecule or some solution over it. Okay. Now, will there be some current? The current will depend on the type of the material that we have, right? If it is, it allows current to flow, it will flow. And in general, some current will flow. Okay. Now, since there is a path and mostly a sample or analyte, we will say analyte is there, some current will flow. Now, it is saying that for this, we can only measure the DC resistance of the material placed on it. For this sample, we can only and only measure DC resistance of it. Is it true? Anyone, please? Hmm. Pavitra Babu, are you there? Yes, please speak up. Varsa, what you think? Okay, since you are from electronics background, right? You are in EC second year, right? Okay. Then what kind of measurement can be done for a simple material? Like if there is a material and we can connect it using two electrodes, what things can we measure for it? Yes, and so current flowing through it, and yes, and this is for DC analysis. And what about AC? If we have put an AC voltage across it, what will happen? Like in case of DC voltage, we have potential and the current. Similarly, for AC, we have potential and current. It's fine. But in that case, that instead of resistance, we have impedance. Am I right? Okay. So we can applying an AC voltage, we'll be able to find the impedance also. Okay. So it is not limited to DC resistance. We can even go for uh, using a AC here. Instead of putting plus and minus, we put an AC here, and we can measure the impedance, change in impedance. Okay. And in case of analytes, where like we have a lot of factors playing part, impedance is more relevant. And as if you see the lectures also, sir discusses at one place that we can either go for DC resistance, or in some cases we can even go for impedance, so that this pa- uh, parasitic capacitance and these things can be removed. Okay, so now will it be true or false? False, because we can go for some more things also, right? Now let's come to problem 6, that is the term VOC have been talked a lot in the course. What does VOC stand for? Variable oxygen concentration, volatile oxygen compounds, variable olfaction calibration, volatile organic compounds. Organic compounds. Okay. Can you give some example of volatile organic compounds? Yes, butanol, propanol, and what is the meaning of volatile? Anyone? What's the meaning of volatile? Yes. So volatile generally means a bit unstable. Okay. So very easy to evaporate. Like when we put it, it is in liquid phase, like acetone and all. I think I put, yeah, formaldehyde, benzene, acetone, methane, trichloroethylene, and there are many more. Okay, if you put it in the open environment, like even petrol, if you put in the open environment, after some time, you will see that it evaporates. Okay, and these are organic compounds, so they are called as volatile organic compounds, and they are very, very important uh, in detection of many diseases. If we check that, in case of some specific disease like asthma, diabetes, and this, in our body, such volatile organic compounds start forming, and at different levels, at different level of that disease, we will have different level of volatile organic compounds forming in our blood or maybe sometimes even in breath. Okay, so detection of these are very important if for non-invasive, like where we don't have to go to prick and check in the like take out a syringe of blood, and then that is the general way we are doing till now, that we take out blood from the person and we put it in some uh, analysis and then we get the results. But what we if we can tap this small, very small amount of VOCs present in our maybe our breath to detect. So in that case, we will not have to invasively prick someone or someone like we will not have to take out blood, cut. Nothing will be required. We will be able to detect, and that also very easily and at a very early stage. That is why these VOCs are quite important in case of biosensors, and a lot of work is being done to make to detect VOCs. Okay. Any confusion till here? Okay. Right. Okay. Four. Okay. Let's. Yeah, circular. We did now. This one. Y- Yeah. Actually, I kept one extra slide there. That's why. Okay. An oxide layer is deposited on a silicon wafer before deposition of metal layer. Like sir said, we had silicon and then we deposited SiO2, which is an insulator. Silicon is a semiconductor and SiO2 is an insulator. Okay. This is usually carried out to limit the effect of like after this some metal were deposited, actually full deposition, and then we patterned it. So let's say that some metal electrodes or ID pattern was made over it. Okay, this is usually carried out to limit the effect of bulk silicon wafer on the conductivity of the metal film. Is the above statement true or false? Like we are saying that so that this silicon does not take part in the conduction, like we discussed here, no? Here, that the conduction is to be through the analyte, through the sample. Okay, so is it true that we are here doing it to remove the effect of silicon? Is it true or false? Yes. Anyone? I think there are many people who have just joined. They are not able to listen to me. Are like, am I audible to everyone or just some people? Okay, but like many people, they are not able to respond. Mm. Swati, Swati Murugesan, am I audible to you? Okay, not an issue. Okay, so what will it be? It will be true or false? See, if we are not using, yeah, it will be true because if we are not using SiO2, certainly the silicon will take part in conduction. And as I said, that a very basic reason of using silicon is that the silicon MEMS based technology is already at a very advanced level, and uh, we can take advantage of it. Okay, so here though silicon is not part of our sensor, is but silicon will enable us to do a lot of other things like the patterning. We will see in the subsequent lectures like week 2, week 3 and all, how lithography is done, how this patterning is done, that is even a very basic part of basic electronics. And since now electronics industry is already at a very advanced stage, we can take the advantage of using that same facility to make our sensors. That is why we go for silicon based devices. But here, since we don't need the conductivity of silicon, we mostly want the conductivity happening through our analyte. So we put a SiO2 layer, that is an insulator, and that is not put, actually that is grown. We will check how this SiO2 layer is grown over, like it silicon is converted to SiO2. How is it done? That will be seen in oxidation part. Okay, so it is true that it is made to uh, limit the effect of bulk silicon. And you must have seen that first we made a heater. Okay, in case of heater also we needed a SiO2 layer, and then after heater we made the IDE pattern, so that heater and IDE does not short. There also a layer was used, that can be silicon or some other passivation layer like silicon nitride and these things. So it is like we have a thick layer of silicon, uh, though not very thick. It is 200 300 micron, something like in around 350 microns. But above it, we are if we make the deposition of maybe nanometers, 200 300 nanometers. So for them, for 200 300 nanometer layer, this whole 300 micron will be very thick, and it will take part in the whole process. To isolate it, some layer of insulation is used, maybe like 400 500 nanometer or 1 micrometer, you can say. And above it, again, our desired heater is made. And after that, we again need to isolate it. So again, 200 300 nanometer of some isolation is put, and then again the electrodes are put. This is the process, and this is used to isolate one layer from another layer. And many a times you will see that in case of biosensors, we go for maybe 4 5 layers maximum. But in case of electronic devices, sometimes 200 300 layers can be made. Layers of processes can be done for making transistors. Okay, so this is the advantage, that we are at a level where we can make 200 300 levels, and that also with very sophisticated instrument. So making these using the silicon fab, it will be very easy, and that is the reason we go into silicon. Now again, the same question, I think, rephrased. Resolution means the smallest change in input which a sensor can detect and express as output. Is it true or false? I think we are repeating this question, right? Is it true? True. Because we have already seen the minimum change we can detect is known as resolution. So it is showing as smallest change in input that can be expressed as output. Sometimes it can detect, but the output is very, very small. That there we cannot read. So in this case, then the resolution is above it. Okay. So the smallest change which we can easily detect is known as resolution, and it is true. So resolution is the ability to detect and represent fine details or variations in the input. Okay. What is the ideal base resistance of an interdigitated electrode structure? Anyone? We have given a hint of this already. That we have an electrode. Okay. Infinity. Why? The question is why. Okay. We have a structure like this. Okay. And we have seen that actually we already have isolated the back context, or we can say that silicon we are not using. Okay, so this is freestanding, and there is some gap between this, right? So ideally, there should be no current flowing through it. And if there is no current flowing through it, the resistance is very, very high. Okay, or we can say this area is actually an insulator, and for an insulator, what is the resistance? Very high, or yes, please speak. You're saying something. So very high, or we can say infinity. So if we are going for an ideal ID pattern, it is having an infinite resistance. Okay, so if this is an ID pattern, and in this case, you see this is not made on a silicon wafer. This is made on a flexible substrate. Okay, so sometimes like nowadays we are even using different kind of substrates. Okay, so here you see these are actually very very close, but if you see it properly, they are not shorted. They are at some distance. Maybe the distance is in micrometer or nanometer, but still there is a distance, and that is why there should be no current flowing through it, and that it is having an infinite resistance. Okay. Now you must be remembering this image from the lecture. A sensor was used to measure the weight of the housefly. A dead housefly was put on this sensor. The image showed a housefly sitting on the sensor and pads to measure the resistance corresponding to the weight of the housefly. What was the characterization technique used to capture the image of the housefly? Like, is it a normal photograph? Like, can we take it from our mobile phones? Can we take such small structures from our mobile phone? Is it possible? Not possible. So, some method was used to measure this. And what was it? Was it scanning electron microscope, atomic force microscope, optical profilometer, or none of the above? Anyone? Yes, please. Anyone remembers? In fact, if you see the name itself, you will get an idea what it was. Anyone knows how an scanning electron microscope works? S- Anyone? Please speak up. Okay. So let me explain. And I will tell how these three work, and then you tell me how, like, which one will be the best thing to take this image. In a scanning electron microscope, uh, on the object, electrons are bombarded to it, you can say, electrons, and then they reflect back. And their reflection, like just like light, okay? It goes there, it reflects back, and then an image is formed. But since with electrons, we cannot see colors like there will be intensities, like how dark it is or how light it is, and these structures will be reflected. And that is the not exactly this thing, but that is the basic way an scanning electron microscope works. Whereas in case of atomic force microscope, on the sample, if this is a sample, there will be a probe like this, and some uh, here there will be some electric, like it will be very close, and there some current will be flowing through it. So near that some current flows, and it will move over the surface one by one, and then with the change in the uh, current flow, we can see how what is the surface morphology like, the surface is like. Whereas in case of optical profilometer, that is lens based optical thing, and there also some tip like structure is used, but actually there this instead of this current, there will be some light over it, and it will reflect. So when it will move over it, if it is up down like that, the light will change, the reflection will change, and according to that we will get the optical profile of the area. So now based on this three, uh, which one will be the most appropriate option to use the image of, like take the image of such a structure? Anyone? Scanning electron microscope. Why? Because we first thing is that this structure is not in a plane. Okay, it is a three-dimensional structure, you can say. So we cannot move some like some probe over it. It will be very difficult. Like, and that also a bee is a very big house fly is a very big thing. Okay, compared to the tip, like the tip is in microns. Okay, and that is why scanning electron microscopy is the best suited for hair. And it, in fact, here scanning electron microscopy is used. Okay, and if you can see that there are some markings there also, like what is the resolution, though it is very big. If you go in details, you can even zoom in some part of this, and you can see very fine details of it using scanning electron microscope. And the resolution will depend on the size of the electron, and size of the electron is fixed, which is in some picometers. Okay, so we can very easily see nanometers and these things. Okay, now biosensors detect which of the following biological components: cell, protein, nucleic acid, or all of the above. Anyone? Please speak. Don't be shy. All of them. Biosensors can be used to detect cells, some specific kind of cells sometimes. Protein. Protein are very good biomarkers. When I am saying about biomarker means some specific molecule related to some specific disease, some specific condition, you can say. Okay, like you must have you must have checked, got your blood group checked. Okay, okay, that is a biomarker that it is present or not. Okay, such things uh, are called as biomarkers, like A, B, and Rh. These are biomarkers. Okay, so they can be used to identify a lot of things. Not they are antigens, but we can say for if we are going for some diagnosis based on such factors, then they can be considered as biomarkers. Biomarkers can be protein, nucleic acid, or some specific kind of cells, which can be used to identify that if this is present or if this is absent, then what conditions will be there. Okay, we'll be reading this later on. So the biomarkers can be protein, nucleic acid. Nucleic acid is anyone knows what is a nucleic acid? I think biochemistry you must have read about. What is a nucleic acid? Anyone? Yes, please. Anyone remembers what is a nucleic acid? Okay, this is something you should read. And remember, when we say DNA or RNA, here Na stands for nucleic acid. Okay, deoxyribonucleic acid uh, and ribonucleic acid. Okay, so try to recall this thing so that it will be very easy for you people to understand the subsequent week. Like just know the terms what they are. Okay, so the answer will be all of the above. Okay, which of the following are the characteristics of a good sensor? We have already discussed it a bit. So anyone? Yes, anyone? Please reply. All of the above. Five. High sensitivity to measured property. Is it right? Like it should be very highly sensitive. Okay. And then insensitive to other application property. Is it right? Yes. So this is correct, right? And this one is also correct. Then is zero influence of measured property. Yes. So zero influence of measured property. So what does this mean? Should there be zero influence of measured property? Anyone? Yes. With zero influence of measured property, what we mean is that once the thing that we want to measure that is removed, the sensor should come back to its initial property, like its initial, uh, you can say its initial position or the base resistance or the base level. So is it a property of a good sensor or bad sensor? Yes. This is a good sensor. So all of the above should be the correct answer, right? A sensor used to measure the quantity of pressure when applied to an object is called pressure sensor, light sensor, force sensor, or sound sensor. Pressure, certainly, the pressure we are measuring, it's pressure sensor. But along with that, uh, what is a light sensor? What if it detects a light sensor? Light. Okay, so what will be the name of that sensor? That will be an optical sensor. Okay, if it is measuring force, it will be known as a force transducer. Okay, sensors are also called as transducers uh, because they can convert from one form to another form. Like they are converting some physical or chemical changes into electrical changes. So they are also a transducer. Okay, and if it is a sound sensor, it is either called as acoustic sensor or microphone. Microphone is a simple sound sensor, we can say. Okay, any confusion till here? Any doubts? Okay. The output generated by piezoelectric sensor. This word you must have heard in the cantilever thing that sir was showing there. The cantilever was there, and SU8 pillar was there, and there a piezoelectric mat- uh, material was there, and based on this cantilever force, we were able to check the changes here. Okay, so the output generated by piezoelectric sensor is mechanical, electrical charge, chemical, or all of the above. Yes, electric charge. So, how electric charge is generated in this case? Since it is fully a mechanical system, right? So, when we are talking about piezoelectric sensor, we are talking about piezoelectric materials. Okay, and what is a piezoelectric material? Anyone remembers? Yes, anyone? Piezoelectric materials are some special materials that will generate an electric charge when some stress or strain is put on them. Like if you are pressing it or if you are trying to like expand it, some electric charge will generate. And this property is used to make the piezoelectric sensor. So here, if there is some force on it, that mechanical force will automatically get converted into electrical change. Electrical, like there will be an electric charge generated, and this we can measure, and that is why we are going to measure the electric charge. Okay. While fabricating a sensor that has both microheater and interdigitated electrode, this is what we saw, that we had a microheater like this. Yeah, let's make it like this. I am not able to draw it properly. Okay, we had a microheater, and then above it there were ID pattern, interdigitated pattern. Okay, that is what was on there. A thin layer of oxide is added in between the microheater and ID. Okay, so there is heater. Just I said earlier also, like below also there is a oxide or SiO2. Between the microheater and this ID pattern, there also an oxide is added. Which of the following does purpose does this solve? It is used to avoid electrical sorting between the microheater and ID. It ensures uniform distribution of heat generated by microheater. So, like whatever the heat is there, it will distribute it uniformly. Is it both A and B, or neither A nor B? Or is it A or B? Yes. Anyone? Both A and B. Okay. Uh, how? Like A, are you sure about it? That it is to isolate. This we have already discussed. About B. Mm, yes. B. Can it uniformly distribute the heat? Yes. Can it uniformly distribute the heat? See, silicon dioxide is a insulator. Okay. And an insulator, both in terms of SiO2 is electrical as well as electrical insulator as well as thermal insulator to a bit. Okay, not much. And there are some more like this. You can say that silicon actually the orientation matters a lot. Okay, so in one direction heat flows, other direction it does not flow, somewhat like that. Okay, so let's not go into that part. Okay, so it is an insulator, and if it was to ensure uniform distribution of heat of the heater, then what will happen that this heat will actually try to flow throughout the system. Okay, we want localized heat. In case of sensors, we generally want that area should only get heated, not the whole area. Okay, and sometimes uniform distribution is not needed. Okay, and generally SiO2 is used not is not used for any kind of heat distribution, but for isolation of the electric like isolation of the microheater and ID patterns. Okay, anyway, this is something that we'll be seeing later on when we'll be making the like we will be seeing how these sensors are made and all. Okay, so after this, any questions related to what we have seen or any other general questions from the course uh, covered till now, you are free to ask. Anyone, please feel free to ask. Don't be shy. This whole purpose of the live interactive sessions is that you are able to ask questions, you are able to interact, you are able to put forth your ideas and get clarification. So feel free to ask. It should enhance your learning. Like doing the questions, like you can get it anywhere. Okay, even searching on the Google, that will be fine. But discussion is what is intended from this. Anyone? We still have a lot of time, so you are free to ask. Yes. Any questions? Okay. So I think that's all. Uh, Thank you all. See you all in the next class. The class will be Tuesday, 6 to 8 p.m. Okay. So thank you all, and I'll be here for some time. For any questions, you can ask me.